So welcome to Friday, the last day of this workshop. We've still got some really nice sessions this morning, so I hope you can stay around to the end. But we're going to start off right now with a science highlight talk, Piyush Mehta, talking about transitioning to supportive industry. So, Piyush.
There's some notes here. I assume they're not for me, but good morning, everyone. Thanks again, Mark, for the introduction, and to the committee for the invitation to talk here. So the title may seem fairly generic to some people, and that was intentional, but I'm going to kind of narrow it down a little bit for everyone. Satellite industry perspective, this is primarily going to focus on thermospheric density and satellite drag. My group's been doing a lot of work around the drag problem, including drag coefficient modeling, driver modeling, and density modeling for the drag problem. So this talk, I'll kind of focus and narrow it down on the density stuff, which I think is likely going to be most relevant to this crowd and community here. So we'll get started. Before I advance my slides, I want to acknowledge the support that my group has received over the last 5-6 years from various agencies, including NASA, NSF, IARPA, and most recently the Department of Commerce. A lot of the work is focused around satellite drag. So why are we suddenly talking so much more about satellite drag? You know, this satellite drag has been a problem ever since we first started exploring space, right, back in 50s and 60s. But there are a few things that happened in the more recent past that have kind of brought this problem of satellite drag again to the forefront. HASDM, as you may know, is the current operational standard, and I'll give you a little bit more details about that. Has been doing fine so far, depending on who you speak to, I guess. But if you notice the charts on the right there, on the top you'll see the distribution of the objects in space, depending on the source or origin, right? And so you'll see in the last few years, the commercial side has basically taken over. As a result of that, if you look at the bottom histogram. Historically, if you look at the years coming over the last couple of decades, coming from bottom to top, you will see that faint. There is no laser pointer here. Okay. You will see that faint green line at about 750 kilometers, which is where most of the objects were historically, up until more recently, about 2016, 2017, when you will see that the density is significantly larger at around 400, 450 kilometers. And so what that has done is that has made our operations a lot more sensitive to thermosphere, a lot more sensitive to space weather, and a lot more sensitive to drag. And so that's why the satellite drag problem has really come to the forefront in recent years. And as you can, as I mentioned, you know, this is primarily driven by the commercial space economy. I'm sure you're all aware very much so about the mega constellations that are currently in space or in orbit, as well as the planned ones. We are already at 10,000 active satellites. That's pretty much 5 times what we were about even a decade ago. And that's expected to grow another 10 times or more, right, by the end of the decade potentially. And this, like I mentioned, has transitioned the density of the objects from LEO or high LEO to LEO and very low LEO. There are missions planned towards very low LEO, 200, 300, 400 kilometers, where the operations become even more sensitive to drag. And so this is nothing new. You know, drag affects every part of operations. The major uncertainty, as we all know, is density. There are other factors that impact drag in operations as well, for example, the drag or ballistic coefficient. But like I mentioned, I will focus today's talk on the density side of things, given the venue and the crowd. So how are we doing things today? Like I mentioned, HASDM, the high accuracy satellite drag model, is the current operational standard. It's actually, while in its name it says model, it's actually not a model, but it's a framework that uses the empirical JB 2008 model as the background. And it has a lot of other characteristics, including generating the TLE catalog as part of operations. But the biggest limitations are it's limited to DoD use, so it's not available to commercial operators. It's low fidelity, basically climatological, and it does not provide robust uncertainty quantification, which in the light of the mega constellations that have come about and sprung up becomes an increasingly more critical piece. And so what we are trying to do, and this is where it comes to transitioning science to operations. The community here, which is all of you, have done a significant and a phenomenal job at improving our models through scientific investigations that include whether it be the density estimates from the high accelerometer, the high cadence and high sensitivity accelerometers on board some of the satellites, whether it be other missions like TIME, GOLD, hopefully GDC and Dynamic upcoming, experimental investigations, as well as geospace coupling. And I put geospace coupling here as a science perspective because one of the requirements to transition things to operations is reducing the computational complexity, including additional complexities as well, but computational complexity is typically the major limiting factor. And we've done a great job at translating a lot of this science into some of our models, including empirical and physics-based models for the thermosphere, but they all carry certain limitations. Empirical models is evident. I mean, they're limited fidelity, climatological, so they don't capture the important variations that we need to capture. Physics-based models do a better job at that, but like I said, they are a lot more complex, including computational complexity. And so what we are trying to do across some of the projects, including the more recent Office of Space Commerce project, is trying to leverage state-of-the-art contemporary AI/ML methodologies to operationalize our best physics-based models, right? And when I say best physics-based models, I don't know yet, and I don't think anybody knows yet which model is better than the other. And so we are not starting with the assumption that one model is better than the other. We are trying to do this for as many models as we can, and then let the validation speak for itself, right? So what we are essentially doing, the primary idea is to reduce the complexity of the physics-based models. We are developing what we call emulators, right? These are also models, but models that retain significant portion of the fidelity of the underlying model, but are significantly faster. So in the case of TIE-GCM, the demonstrations that we've made over the last half decade, these models are about 10,000 times faster to evaluate than the original physics-based models. So that makes a lot of things around operations feasible. And so the fundamental idea is, rather than working in the full high-dimensional space of a physics-based model, we compress down the parameter space and really do everything in the reduced or latent space. So as a result, the first step is always dimensionality reduction. We compress the state down to a reduced order state. And then we actually do the dynamic or time series modeling in the reduced order space. That makes the model really fast to run. You can run this, do a 7-day forecast on a standard desktop in a fraction of a second, as opposed to what you would do for a physics-based model. And so you can see that metrics on the bottom right. There are different methods on how we could go about doing this, and there's different combinations. So there are two primary steps, dimensional reduction and dynamic model. You could use linear approaches for both. You could use nonlinear approaches for both, or a combination. We historically started doing the linear approaches, crawl, walk, run kind of approach. And so we did the PCA plus linear state space model back in 2018. We extended that recently to the PCA plus RNN, which is the linear dimensional reduction and nonlinear recurrent network model. And then we are currently working on the nonlinear dimensional reduction and nonlinear dynamic model. I'll have some preliminary results on that. They should be published next month. But we'll get into that. So a little bit of what we've been able to achieve and where we are at right now. So like I said, the 2 steps are dimensional reduction and then dynamic modeling. One of the advantages also for doing this in a reduced state is that it allows uncertainty quantification. And like I said at the beginning, that becomes an increasingly critical piece as we advance into the new space economy with more and more constellations coming online. So bottom left plot is essentially taking the full model, the linear model, and the nonlinear model, giving it an initial state and drivers for the entire year, and comparing how the dynamic prediction works between the linear and the nonlinear reducer or emulator model. DMD, the red curve, is the linear model, blue is the nonlinear model, and black is the true TiGCM output from the full physics-based model run. So you can see the linear models, because it's not able to capture the dynamics very well, starts to diverge. But when we extend that to the nonlinear model in the dynamic modeling regime, it actually understands and learns the dynamics very well in the reduced state space, and then is able to track the evolution of the model pretty well. And so again, a reminder, this only takes the initial state and the inputs for the entire year. Everything else is just the model itself. On the top right, alpha 1 to alpha 10 represent the components of the latent space, which is this once you take the full dimensionality map or 3D cube and map it into the reduced state space, that becomes alpha 1 to alpha 10. So essentially, you take the entire grid of your density, compress it down to 10 values, and then you evolve the 10 values over time, which allows you to do this much faster. But the advantage is now you can train a set of models and then try to characterize the uncertainty, because as you develop these models, and it's no different than having different empirical or physics-based models, each model is going to have different capabilities and performance capabilities at different conditions or input space. And so we leverage the ability of each individual model and combine it into an ensemble. And so that, again, like I said, allows us to characterize the uncertainty, which is something we've not been able to do so far very well, especially for operations. And so that's really another critical piece that we are adding with this operationalization or transition. And hopefully this video runs, but this is this new work that I said we are doing the nonlinear dimensional reduction part and the nonlinear dynamic modeling part. I had to put Harry Potter in there as AI/ML wizardry, just because, like I said, this is going to be published next month, hopefully. And so, so far I'm not able to share any details here, but hopefully, when I present this in the next month or so, I will be able to share all the details, or you can read the paper. And so on the right is a simulation going through the Halloween storm. And before I run the simulation, I want to kind of describe what you're looking at. So the top left is the true TiGCM, the original physics-based model evolution through the storm. The bottom panel, or the column, is on the top, you have the linear model, the linear reducer model, and the bottom row is the error with respect to the original TiGCM. And then the last column is the nonlinear reducer model, and then the bottom row is the error with respect to, again, the true TiGCM. So you will see that both the linear and nonlinear approaches do reasonably well when the conditions are quiet, but when it becomes active, the linear model kind of breaks down with high errors, and then the nonlinear model is actually able to track the system very well. That is also reflected kind of in that plot on the left, where you can see that if you do the linear PCA approach, the errors grow as with KP, because that's where the system grows nonlinear. But with the nonlinear approach, the profile is significantly flattened, and we get much improved performance even during active conditions. So let me see if this one runs. Hopefully it does. So right now the errors are, primarily white or, very faded red and blue, which is low errors. And as we hit the storm, the linear approach kind of gathers and accumulates errors, where the nonlinear approach still retains most of its performance, including going through the second peak, as it will do now. Again, the linear model errors will grow. The nonlinear will grow slightly, but not as much. But the important part here is the true TiGCM model here is running on an HPC cluster. The reduced order model is doing the same thing on a single desktop processor in a fraction of a second, right? The entire process. So that's really the beauty of what we are trying to do here. So this is my last slide. I know I may be running up, running up on my time there. So one of the advantages of the reduced order capability is also that it significantly simplifies data assimilation. So what I'm showing here is an Aussie experiment. This video shows the assimilation from measurements of a single satellite. The thing to note here is that the measurement is directly the state of the satellite, which is position and velocity. We are not converting it to density. There is no geophysical parameter that we are using to assimilate. This is directly assimilating the location of the satellite, the position and velocity. And that is another advantage that the reduced order model provides, that you can directly assimilate a heterogeneous set of measurements into your system. And so you can see as we assimilate a single model, the uncertainty localized around that observation reduces, and then you map that uncertainty away from the observation, and the uncertainty grows standard because we don't have observations there as expected. But then when we start adding more and more satellites, so here what we did is we added 3 satellites first, then we added 5 satellites, and then we added 10 satellites, providing a global distribution of information as measurements. And you can see somewhere between 5 and 10 satellites is sufficient, provided they are distributed correctly, is sufficient enough for you to reduce the global error of density as well as the global uncertainty of density as you do operations. So this, like I said, in combination with the reduced complexity and the uncertainty quantification capability, this is another major advantage of the reduced order modeling approach that we are employing to transition these operations. And we have continuous feedback and advice from some of the operators, and I think I had them on the slides, SpaceX, Amazon, Leo Labs. They are actively participating in this project with us. And so everything we are doing is focused on delivery to operations and integration with operations. So with that, I will stop because I know Mark's getting anxious because I'm running out of time, but I will be happy to take any questions. And Jeff has a question.
Thank you, Piyush, for that great talk. Question here?
Yeah, great talk, Piyush. Thank you. I was wondering if you could say that the problem that you're working on with regard to drag, and the reason why the reduced order modeling may work so well, is because the drag problem doesn't depend on high order fidelity in the model because of the integrated nature of drag. And could you?
I wouldn't quite put it that way. I think the perturbations are important, the structures are important, and the reduced order model works, and that was kind of the point of transitioning from the linear to nonlinear approaches. With the nonlinear approach, you can actually retain a lot of that fidelity as well. So we are really losing very little, but gaining a lot in computational cost, if that makes sense. What you're saying in terms of integrated time is an important factor and potentially can be neglected in the orbit determination side of things, but when you're forecasting into the future, that should not be the case. You do want to capture all those variations, all those scales, and that's why I still believe that physics-based model is the right way to go. It's just the complexity kind of overwhelms the operators, so they cannot really employ them in operations, if that makes sense. Yeah.
Thank you. I think we have time for one more quick question, if there is one. Actually, I have a question.
Yeah.
So, you showed that the model did really quite well during a large storm, but you have to train this satellite drag GPT on storms. So presumably the events that people care most about would be the ones that you would have the least training data for.
Yep.
So does that turn out to be a problem? Or?
That is right. So that's one of the, if I can go back, I don't know if they still have my presentation up. No, okay. That is where the new results that I didn't present, how we exactly did it, is we tried to address that imbalance in the data. And that's where we were able to improve the performance during storm times as well. Now, you make a great point. Because it's a machine learning model, like any statistical model, it's only good for the data it's seen, right? And so the advantage here, again, is it's so cheap to assimilate data, we could potentially retrospectively go ahead and assimilate 2-3 solar cycles of data, update the weights of the model so that it reflects performance during those storms. And in the future, really, I think it's anybody's game because all models are the same. Whether it be empirical, physics-based, or the reduced order model, you never know how it's going to perform, because you've never seen it. And, unless it's something you've seen in the past, then you can estimate what the performance is going to be. And so that's one of the reasons why we are also not claiming that this is going to replace physics-based models, in the sense that I think they need to work hand in hand. I mean, obviously, physics-based models have their own challenges as well, but you run this for operations and you continuously validate with physics-based model, right? In the sense that as long as it's looking reasonably good, I think you're good to go forward with the reduced order model, if that makes sense. But having said that, I don't want to also claim that the physics-based models are not going to break down or do something weird. So that's really the point there.
Thank you. That makes sense. I think it was Yogi Berra that said that predictions are difficult to make, especially about the future. So.
Yep.
Let's thank our speaker once again.
Thank you.
So our next presentation is an early career highlight by Hainan Wu. It's called Mesoscale Gravity Wave Impacts on the Neutral Wind Dynamo Using General Circulation Models. Thank you.
Okay, thank you. Thanks to the CEDAR Steering Committee to give me a chance to present our recent work on this topic. And before I start, I would like also to thank my co-authors here, collaborators from University of Colorado Boulder, from JHU APL, and other NASA NCAR labs from CISO. So my today's topic is about the my today's topic is about the mesoscale gravity wave impacts on the neutral wind dynamo using general circulation models. And this work is supported by CGS, Center for Geospace Storm, NASA Drive Center. So let's go. So the first question might be, what is a neutral wind dynamo? So from Richbeth 1971 paper, we got this definition. Neutral wind can drive plasma across the field line, which leads to charge separation. And the charge separation leads to electric polarization, electric field. And this can only be neutralized by current flowing along the field line and in the E region. So if we write down the governing equations, we have current continuity. The first equation, as I showed here. And in this work, we are counting the Patterson and Hall Patterson current, Hall current, and field aligned current. Also, we are assuming electrostatic situation, so the electric field can be written as the gradient of a potential field. So as we also assume infinite parallel conductivity, so we are able to simplify the whole model into a 2D model instead of simulating the whole 3D model. And the first equation is what we get by integrating the current continuity equation along the field line. And this is the two-dimensional problem. And look at the right-hand side. We have this Q term and this J parallel term. This Q term represents the driving forces from neutral wind impact, and the J parallel term represents the impact from the magnetospheric current. So this is our model, and this is the equation we are going to solve. And how to solve this equation is by certain kind of method, and certain kinds of numerical method. And this is this figure shows the spatial grid we are using to solve the previous partial differential equation. And we are setting up grids along the field lines, and each grid covers a distinct field line. So we calculate the currents in the volume and out of the volume. The detailed grid setup can be found in Multi and Richmond 2017. And I'm going to skip the details of this of the grid setup here. Detail can be found, or people interested can refer to that paper. So one may ask, why is there a new model? What is the difference between the old and the new dynamo? So I here listed some points. The old dynamo uses a finite difference formulation, and the new dynamo uses a finite volume formulation. And in the old dynamo here, an important point is that in the old dynamo, the field line integration is not carried out strictly. It is approximated by assuming some quantities varies in the certain form along the field line. That leads to this third point. In the old dynamo, the current continuity is not strictly followed. It's not strictly satisfied in the whole domain, and that is no longer a problem in the new dynamo, since in the new dynamo, the field line integration is carried out strictly without any approximations along the field line, and the current continuity is enforced global-wise. Also, in the old dynamo, we have limited choice of resolution, but since the new dynamo has a flexible grid setup, we have a lot of choice of different resolution combinations. And the last point mentions the numerical matrix solver here. The old dynamo uses a serial iterative multi-grid solver. The new dynamo uses the parallel direct sparse matrix solver, which can largely increase the speed of the calculation. So as I mentioned, the wind has a Q term that affects the neutral wind dynamo. So among all those possible neutral wind perturbations, I'm going to talk about the gravity wave impact to the neutral wind dynamo. So here is our numerical experiment setup. We choose the Tonga volcano eruption on January 15th, 2022 to demonstrate our new model. And TIE-GCM, as usual, TIE-GCM 3.0 is used to run at 1.25 degree horizontal resolution and a quarter scale height. Let's go back. What makes this new run different is that we are using the lower boundary forcing from a WACOM-X simulation, a WACOM-X spectral element simulation, instead of the empirical background using either GISWM or CTMT. So we are considerably studying the smaller time scale of the physical processes. Also, the last point is that we are comparing the performance of the old wind dynamo and the new wind dynamo. So here is the lower boundary that we have put into the model. This shows the potential height, geopotential height at 97 kilometers, which is the TIE-GCM lower boundary. And this concentric ring pattern here are from WACOM-X and used as the model input. And now in this movie, we are looking at the TI-GCM responses. So this is vertical wind at 300 kilometers. So clearly we can see that this concentric ring pattern are from the imposed lower boundary forcing. So next slide. Talking about the neutral wind, neutral responses, let's look at ion drift, the electrodynamics responses. So here is the comparison of the old dynamo, which on the left figure, and the new dynamo, which is at this middle figure. So comparing these two, we can see that the new dynamo has a significantly sharper boundary of this concentric ring. Well, although these concentric rings exist in the old dynamo, it's largely smoothed, likely due to the field line, inexact field line integration in the old model. So if we compare, and if we also compare the difference between these two models, we see that the difference of the vertical drift are on the order of 30%. So next slide. The vertical drift are on the order of 30%, and this is a quite significant difference when we can only considering the wind or neutral wind forcing into in the wind dynamo model. So if we look at the other quantities, for example, the zonal drift, we also see some difference, although they are pretty covered. The color bar is pretty saturated due to the equatorial electrojet. But what I can say here is that if we subtract these with the new dynamo with the old dynamo, we get this difference. We can see that generally the equatorial electrojet is larger in the new dynamo than the old dynamo. So we are also enhancing the equatorial electrojet in the new model, new grid setup, new model. So let's switch a little gear a little bit from the new electrodynamics into the ionospheric responses. This is the electron density at 300 kilometers. But this time, we don't really see a big difference between the new dynamo or the old dynamo. The differences are on the order of 10%, so relatively minor. So that's all we get, and this is the take-home message from this talk. So the new wind dynamo has been integrated into TI-GCM to replace the old wind dynamo, and it better resolves the sharp ion drift gradient caused by the large wind shear and in the lower atmosphere, near the lower boundary. And on the other hand, the ionospheric responses using the new wind dynamo is still similar to the old wind dynamo. So that leads to, the ionospheric responses is a minor impact. And I also list some future items here. Currently, the neutral wind dynamo, the wind dynamo hasn't included the magnetospheric current input, and this is our ongoing project. And if after we incorporate the magnetospheric current input, we will get this so-called global potential solver, and this will also be integrated into TI-GCM, and this will presumably better resolve the penetration electric field during storm time. Also, we are going to integrate this global dynamo solver into our multi-scale atmosphere geospace environment model. And please stay tuned to our CGS announcement, and thank you.
Thank you, Hayanan. That was yet another really nice, clear, and useful talk. I really enjoyed that. Thank you. Time for one or two questions. Oh, question over here.
I think Doug raises his hand.
Thank you,
first.
Hanan. This is really good achievement, and you calculating the dynamo when you have neutral wind disturbances, gravity wave kind of thing. I was wondering, and during storm times, we know there are gravity wave associated with the heating in the Aurora region and propagating globally. Now, if you have wave generated in both hemispheres, propagating to equator, are you going to have very complicated patterns? So have you tried any kind of storm time gravity wave impact?
Yeah, this is the question. We are not developing the whole model yet. So we are currently only considering the wind-driven effect and the high latitude magnetospheric current input. I mean, the storm impact hasn't been incorporated into this model yet. So this is our ongoing project, and we believe that will cause quite a difference between the old dynamo and the new dynamo.
Thank you.
Yep,
excellent talk. It's really important to get the dynamo good. I have a question about the Hungatonga event. Guan Li showed with swarm data that the electrojet reversed direction. Do you see that in your simulation?
You mean the electrojet switch from east to west, west to east? I didn't take that well, this simulation only performed for 2 model hours, so I probably missed that point. Probably I haven't got that point, but we will see that we will definitely take a closer look at this equatorial electrojet reversal. Thanks.
Thank you for that. I think we do have to move on, but let's thank our speaker once again for another really good talk. All right, next up we have 2 talks about new missions that are either operating now or about to operate. The first is by Ludger Schierles, and he will be telling us about the OR mission. Thank you.
Yeah, good morning, everyone. And it's my pleasure to tell you about the atmospheric waves experiment, or the OR mission. And of course, I'm not Mike Taylor. I'm Ludger Schierles. And unfortunately, I took over as the PI of the mission due to the necessity, due to the progression of Mike's illness. But I have to say that all the credit, all the success so far of this mission, the credit for this really belongs to Mike Taylor and his team. I'd like to point out here Dominique Potet, Eugene Zhao, and I also like to mention the Space Dynamics Lab, who not only built and designed the OR instrument, but also manage the mission. So what is OR about? Well, OR is the first dedicated NASA mission to investigate the global gravity wave properties in the upper atmosphere, that is in the mesosphere near the mesopause, and to also look at the impacts of these gravity waves on the ionosphere-thermosphere system as a whole. So basically what we just seen in the simulation, for example, that we've seen with the new dynamo solver, where concentric gravity waves due to convective activity, for example, introduce space weather. So what is the connection of the tropospheric weather? How does it influence the space weather? That's the broader question that we're trying to understand with the OR mission. Now, of course, we have several science objectives, 3 objectives that center around this theme, that center around gravity waves in the mesosphere and their effects on space weather. So we want to quantify the seasonal and the regional variabilities and influences that the gravity waves near the mesopause exhibit. We want to identify the dominant dynamical processes that control the gravity waves. Where do they come from, and what do they, well, what is the physics along the propagation? And then look at the wider role of them on the entire ITM mission. And you're going to see, there are, of course, the observations from all, but there's also modeling involved in there. This is, of course, a very challenging problem. Yeah. Now, the ALL mission is up and running. It was launched about a half year ago, November 9th. We were, as a team, all down at Cape Canaveral watching the launch of a Falcon 9 rocket to the International Space Station. That's where the ISS is. That's where it's located. And you might have seen, you might have seen these guys at the meeting here. We took several of our undergraduate students there. We were there for several days doing outreach activities. This is Dylan and Connor. Say hello to them when you see them here. They did a fantastic job educating the public at the Cape about the mission. So this was the beginning of November. We were installed then over the next 10 days, and about 2 weeks later we had first flight. This is for Mike Taylor, of course, here. I'm sorry. To go back here. Mike Taylor. Well, I don't know. Does this work? Yeah, Mike Taylor here getting very excited, looking at the first light during the first day of observations. We turned on the instrument on that day, and we have not turned it off yet. We're taking observations every second, for the past half year. And during the first flight, I'd like to share a couple of images that we saw during our visit here. This was to the Mission Operations Center at SDL. And this is one of the images, that we looked at. These are, in fact, these are several images here stitched together. And you see here a swath 3,000 kilometer in length, 600 kilometer in width, with very active gravity wave activity. This is over the northern Atlantic region on this first day where we looked at the data, one of the first orbits. And you see gravity waves of all scales here. There are, if you look along this, again, 3,000 kilometers, there's scales of 1,000 kilometers, there's scales of hundreds of kilometers, and there's scales of tens of kilometers on this image. So this was one of the first orbits. The next orbit, the space station passed over the Caribbean, and there was a strong thunderstorm activity, strong convective activity going on over that region, over Venezuela. And what we saw were these set of concentric rings in the observations. Looks a little bit like an undergraduate diffraction experiment, almost, where you drop pebbles in a lake. These concentric rings, and again, we have seen in the prior presentation the space weather effect of these. They influence the electrodynamics, they influence the plasma density, very important. So this was the second orbit. This was the third orbit, basically. We were passing over the North Atlantic here. And in this case here, look at this structure here where the gravity wave activity dramatically changes from one region to the next. Most likely this is associated with a Bohr event or with some front event. So this was all during the first look at the data, the first slide, and we've seen many of these cases since. So what is the measurement concept then? How do we observe these gravity waves? Well, it's based on the Advanced Mesospheric Temperature Mapper that has been around for over a decade now, that Mike Taylor had employed at many locations around the globe on the ground. He had placed them on an airplane. And traditionally, it's the AMTM uses three emission lines in the OH spectrum. That is P12, P14, and the background. And we're also using these three emissions, but the novelty of the ALL instrument that we're also use a fourth line that's in the Q20 band. That's the Q11 line, and we use that. Since we're looking from the space, we have to worry about reflections from the ground. We have to worry about reflections from clouds, and we use the Q11 line to correct for these reflections. But the basic concept is the one from the AMTM, so really proven technology. Yeah, and yeah, so we're, whoop, I'm not too good at this. Okay, so we're looking at the air glow layer at 87 kilometers with the AMTM, observing the spectrum in the OH, and then at each second we're getting images of the OH emission lines, you know, where we see the background, we see P12, P14, and the Q line. So these are images with a field of view of 600 by 600 kilometers that we then combine in the traditional way how this has been done over many years by combining the P12, the background, and the P14 to give us the temperature. And as I said before, we're using the Q line to do corrections on that for reflections from clouds and corrections from clouds and the ground to give us images of the temperature. Now these images are again on a 600 by 600 kilometer grid, 2 kilometer resolution, which we then can stitch together along the path of the ISS to give us a swath along the entire night side orbital track. So these swaths then have a length of up to 15,000 or 16,000 kilometers and 600 kilometers in which, so we see gravity waves on many, many scales in these observations. Yeah? And how long are we gonna do this? Well, it's a 2-year mission, so we're gonna measure for 2 years on the ISS. We're only taking on nighttime observations. Of course, you know, that's a limiting factor, but with the ISS, we're getting 15 orbits per day, and we get the full global coverage between plus minus 55 degree latitude every 4 days due to the orbital inclination and the precession of the ISS. Again, we have a 1 second integration time for the measurements. So every 1.1 second, we get actually a temperature map, and we get also the radiance map. And we have a 600 kilometer field of view, as I said. And with that, we're planning to resolve gravity waves from 30 to 300 kilometer horizontal wavelengths. But as you have seen already in the cases that I showed you, we think that a long track, we can get much longer wavelengths, up to thousands of kilometers. And from the resolution, we have a 2 kilometer resolution. We also anticipate to get smaller wavelengths than the 30 kilometers. As part of the OR mission, we also have a modeling component included, as part of the project, and we have, for example, the NavGem model, part of it, to give us the background field. We have WACAM-X, just seen an example of that in the last talk, included as part of our project. You've all seen, throughout the week, the spectacular magic simulations, and we're going to use those to give us information about the connection of the gravity waves that we see at 87 kilometers and the space weather effects. And we also have CG Cam from GATS, and you also probably have seen some simulations during the week from that model. Yeah. So, of course, the data, this is a NASA mission. We're going to make this data available to the public as in various levels, level 0, all the way to level 3 data products that are processed at the Mission Operations Center at STL or the Science Operations Center in Logan. So these are raw images all the way to process data, temperature swath along the orbit. Now here's an example here. You've seen this before, a temperature swath or a brightness swath, 15,000 kilometers in length, 600 kilometer in width. And of course, this is geolocated. You can project it on the map. This is just one orbit here, or in temperature. This is in brightness now for 15 orbits, where you fill up the globe. And as I said, after 4 days, we're filling in the gaps in between. Yeah. We have done some comparison of the temperature data with ground observations so far, with Burr Lake observations. We have a ground AMTM there, and also Titus was running his LiDAR. You see here a very good agreement here. You can see this better on this one here, where we show the air temperature versus the observed ground-based measurements, and we have a good feeling about the accuracy of the temperature. Now, we also started to use the data for science observations. This is for an investigation of the gravity wave variance, the activity during and before, during, and after a sudden stratospheric warming event. Yeah, so I want to leave you just here with the status right now. I'm running out of time, as I see Mark coming up here. Just to, so we're successfully launched, about half a year ago. We had first flight, just a couple of days later. We've so far observed, of course, thousands of orbits, millions of images that we have collected, and we're gonna make this data available very soon. We're hoping by the end of the month or the beginning of the next month, but it should come very soon. And let me stop here.
Thank you, Ludger, and thanks to Mike Taylor too. This is absolutely fantastic. It seems like for as long as I've been coming to CEDAR, people have talked about, flying cameras to image gravity waves from space, and now we're finally doing it like this. So this is really cool. I think we have time for one quick question. Oh, question over here, Angeline.
Hey, Ludger. Excuse me. Thank you for this awesome presentation. All is amazing. My question is, do you guys have a single line of pixels that you're like sampling at every second, or you have like a square image that you're sampling at every second?
Mm-hmm. Well, we're taking, in fact, 4 images every second, simultaneously. 600 by 600 kilometer. It's actually a square on the camera, but it's a 600 kilometer diameter circular image.
So the follow-up question is, do you have any plans to actually get some time evolution of the features, since you have a square image that has some overlapping as you go?
To get what?
Like some time evolution of the features that you're observing.
Yeah, yes, of course, in a very limited sense. We're moving with the speed of the ISS, almost 8 kilometers per second. But of course, we're oversampling the same location. We see them for a 100-second period. So you can't see the wave moving, and we're using that, for example, to get the phase speeds of the waves. Yes.
Thank you for that. Excellent question. But thanks again, Ludger. That was a really nice presentation. All right, our next speaker is Sam Yee, who's going to be telling us about the EASY mission, which is truly innovative and exciting, and I'm looking forward to this. Thank you, Sam.
It's really exciting to see the good results coming out of the OR mission. Congratulations to Mike, Jeff, and all the entire team, the OR team. I would like to spend the next few minutes to talk about EASY. Just like OR, EASY is another NASA-selected mission. We call it Mission Opportunity. And it's scheduled to launch actually in 3.5 months from now. So we're looking forward to its launch, and also excited to see whether we can get the good results, which I believe we will, just like we're going to see today. So hopefully next CEDAR, we come over here to show you the results. So EASY stands for Electrojet Zeeman Imaging Explorers, and it's a mission to study the electrical currents in the Earth's ionosphere. You already heard the previous talk about the wind dynamos, about the interactions between the neutron and ion, the winds, how it generates so-called EEJ, which is equatorial electrojets. But we're also interested in the high latitude. The high latitude also, there's another we call aurora electrojets, which is the closure currents of the the field line current to gigantic current system flowing from the magnetosphere to the ionosphere. And those systems, especially the aurora electric jet, is the closer currents of that actually contain the signature of how the magnetosphere and ionosphere are coupled, how the energy actually being released from the magnetosphere to the ionosphere. So what we want to study is try to understand a little bit more about the processes, how the coupling occurs. And lots of important things, how we actually can interpret the data and understand the coupling processes depends on the structures of the current system we're observing. So all the large current system we have seen before obtained from magnetometer on board spacecraft, which are quite a distance away from the current system. Current flows in around 105 and 100 to 300, 130 kilometers. So the further away from the current system, the spatial resolution get bigger. So the key things is we want to get some kind of measurements with a mesoscale, a bit smaller scales, so we can really discern the physics, what's going on, using the current theory, and also try to resolve lots of debates on the mechanism. So what is EASY then? EASY is a 3 CubeSat mission, 6 U CubeSats, flying in a pearls on a string configuration that uses compact multi-beam instrument, basically one instrument on the spacecraft for multiple fields of view, and using this technique we call the Zeeman sensing technique to image the electric jets. Using this remote sensing technique, we can actually probe the magnetic field induced by the current system at an altitude very close to the current, because we use the proper lines and proper technique. So then that will solve the problem that system, lacking of measurement of smaller scale structure measurements. So EASY will study the mesoscale, the smaller scales one, the spatial structure and temporal, because we use 3 spacecrafts in series. So we can probe the same structure, different timing apart. So this kind of measurement is very important. So you can provide information for understanding of geospace coupling processes. So the main objectives, of course, we are interested in aurora electric jets. First of all, we want to be able to resolve decade-old debate about the substorm current wedges. You can see the different hypotheses, depends on different theory, put it forward, what kind of current system looping, you can see the different 3 hypotheses. And also, we would like to determine to what extent the electric jet consists of whether it's a single smooth current system or actually made of small-scale wavelets. So those are the main objectives we put forth. And all this required a measurement of a smaller scales, also all the action taking place near the magnetic midnight sector. So the orbit's going to be sun-sync, close to the midnight crossing, and then using the remote sensing instrument. So how we actually do it, the implementation scheme, is first we want to make the measurement, map the mesoscale spatial structure and temporal. And then we use this so-called Zeeman technique. I'm going to go give you a little bit more details. And use a 4-view spectral polarimeters and to image the electric jets, as is shown in the middle figures in here. And the 4-view give you observation with a different beam separation shown from 150 kilometers to 500 kilometer separation. We fly 3 CubeSats, and we call it differential drag to maintain, to manage the separation, to adjust the separation. So we can get the timing separation varying from 2 minutes to 10 minutes between spacecraft. And also use the measurement itself, because it's a particular emission we don't look at, allow us to get wind, because the Doppler shift gives the wind. Also look at the brightness temperature to give it a temperature profile. So those are the additional products. This is just a simple comparison, the advantages of the different techniques in here. The ground-based measurements, magnetometers about 100 kilometers away from the sources, and spaceborne 300 or 400 or 500 kilometers away from the current system. But EASY, we use remote sensing technique. And once we pick the right line, you look at contribution function, basically we found that we are measuring the magnetic field perturbation about 80 kilometer altitude region, which is about 20 kilometers below the current. So because of that, so electric jet induced B field, we actually measure it stronger, closer to the current. Second thing, we can allow us to look at smaller scales. The third thing is the B field structure can be imaged with 4 beams, 4 spots on the ground on single spacecraft. If you put a magnetometer, only one measurement. So one spacecraft, we can put 4 sensors on it. And we can actually, bigger spacecraft, we can put more. We can actually image the structure even better. So the technique itself, called Z-mount, if people familiar with the Z-mount technique, basically one of the emission in the presence of magnetic field, certain particular type of emissions, because of the effect of the magnetic field, the blind can split, either central and unsplit, also split line. The split into 2 lines for this particular case. And then the separation, the frequency of the splitting, proportional to the total magnetic field strength. So if you just measure the separation, you can get a total magnetic field strength. But if you measure the polarization state of that, is shown in the figure on the right, then if you measure the full Stokes, then you actually figure out the direction. Function. So using the split, you get total magnetic field, and using the polarization, you get the direction of the magnetic field line, and then using the spectral shift, you get the winds, and measure the brightness, you get winds. So because the resource limited, we have 4 spectrometers on one spacecraft. Each spectrometer is 1024 channels, lots of data rate, and also the power. So we basically come up with very resource-limited type of observation. 1 data collection per 1 orbit. Each data collection lasts up to about 14 minutes. And during the nighttime passes, we do the drive maneuvers, try to maintain the configuration. And during the daytime, we spend time for the spacecraft charging. But then about 14 minutes dedicated to science. One science mode started with, we call it SkyCal, looking at the dark space, and then 9 minutes to 11 minutes of science data collection, and another SkyCal to finish 1 data orbit. So each data sample, 2 seconds. So you can almost see that 1 orbit, 1 data collection with every 2 seconds. And then with summertime, we measure the auroral electric jets. Equatorial time, we measure equatorial electric jets. So we don't have the real data to show you. I can only show you what we expect to see. We call it RZ experiment, what we will get. So I'll use that to show you what kind of data product we're going to get out of, what you should expect. So this is a simulation experiment. We use that simulation experiment to demonstrate algorithm, retrievals, also optimization of the instrument. The first one is rotated. Sorry about that. On this axis, right now, the vertical axis is the frequency, and then the other one is orbital track, about 9 minutes or so. And each one is about 2 seconds. You can see the line actually split, right, about 3 lines. The center line right there is non-shifted line. It's a functional event. If you get 4, so level 1 product is brightness temperature of the 4 Stokes. So you can see that the variation along the track is due to the angles respect to the field line. Your observation angle respect to the magnetic field line. So you change intensity between split line and non-split line. And also right now the top 2 and the bottom 2 are S1, S2, S3, S4 type of measurement Stokes. And you can see that circular polarization on the bottom 2. And based upon those measurements, the 4 Stokes parameters, and one event, one day, we can get the BX, B down, magnetic field down, east and north. And this is the one that every 2 seconds, we can retrieve the data and then compare to what actually reported by camera models. So just to demonstrate how the algorithm works, second thing is we can make the measurements. And then you can see what kind of product we're going to get. So level 2 product, the first level 2 product is the 3 components of magnetic fields, about 9 minutes data event. And then based upon those, that one will show you just 1 spacecraft. Then you have similarly 1 spacecraft flying by, and you have 4 beams like this. Then based upon the magnetic field perturbation, we can reconstruct the best current map. You call it equivalent current map that consistent with the magnetic fields that we measure. And the one on the, again, you rotate again, the one on the left, on the top now, are the one actual input of the magnetic field strength, also the passes, and on the current system on the bottom is the one we reproduce, what we generated based upon the 4-beam or 4-track measurements. Of course, this is just 1 track. Then we're going to have similar map, which is a level 3 product, in the current system, 3 consecutive spacecraft by 2 to 10 minutes apart separation between the 3. So we should expect this. On top of that, each orbit, we're going to get temperature profiles as well as line of sight winds along same orbit flying. You can almost imagine every 2 seconds we have a temperature profile as well. We also have built, I want to talk about the status, of course, and the instrument has been delivered, and it meets all our requirements and delivered to the spacecraft. The spacecraft being integrated, passed all the vibration tests. Right now, in the final stage of we call the TV test, thermal vacuum test. Okay, so in the process of that, all right. And then all three been delivered to BCT and spacecraft integration. All three spacecraft integrated, vibrationally tested, and currently in the TV test. Getting ready to ship to MSS, which is the Maverick space system for integration to the launch. And the deliver, we call it PSR, called pre-ship review, which after that review, a few days later, we deliver the whole package for our instrument with the dispenser all the way to the Maverick. And that, I think PSR, it's going to occur sometime September the 18th or so. So maybe that's supposed to be 45 days before the launch. The launch date right now, the window is October 1st to November 30th. So very quick, 2 months, we're going to deliver the whole thing to be integrated on the launch. It's a right share out of Falcon 9, and the schedule is like that, sensing orbit at certain local. We know the altitude right now is about 590 kilometers, which should last us at least 18 months that we designed up to. And after that, it's up to us to, if still altitude favorable, still good results, we can go for extended missions. But currently it's 590. Exact local time, we haven't heard words from MSS yet. Because it's right share, so we provide our requirements, and they will meet our requirements, but we don't know exact local time yet. So the launch, again, like I said. But we also have a it's not advancing. Can you make the next slide, please? Yeah. Okay. Yeah, that just showed the solar panel deployment test. The next one, we also have built in a very excellent outreach and citizen science program. This is the last slide. Sorry about this. And if you can go up to our website to get more, know a little bit more about our citizen science program outside. And we have an excellent one. We basically fabricated about 600 magnetometer, commercial grade magnetometers, and with a measurement resolution about 12 nanotesla. Each one, the kit, costs about $200. All right. And then this supplement our measurement very well. Our goal is try to distribute the 600 units, 600 magnetometers to all the schools around the nation, especially the ingenious communities. And then there was a teacher conference workshop last week taking place in Navajo country. There's some very, very nice programs in there. And this one, you can, if you know someone, your school, you can go on to the website and ask for it. We'll send you the kit. And kids basically give you all the instruction. You can assemble the kit together. And this is just to demonstrate one of the magnetometer actually present in the high latitude in Alaska during that superstorms. You can see that how well our measurement compared to the regular supermax sites, just to demonstrate the quality of this particular magnetometer. So if you're interested, you have schools you would like us to sign up with us, please do go on to our website. And the last one, I just want to thank you. Also, we look forward to the future collaborations. You know our data products, you know what to expect, and it's going to happen in about 3 months. For the first 6 months, is our early ops, our own cleaning up, and the data will be made public after 6 months. And there's an open workshop coming up, September 25th to September 27th. So please register. Format is going to be either online, virtual, or in person. It's going to be held in APL. Thank you.
Thank you, Sam. You know, it's maybe once in a career that you see a fundamentally new technique and a fundamentally new application of basic physics to explore our field, and that's what EASY is. You know, we haven't seen anything like this before. I think we have time for one super short question, if there is one.
Any question? Yeah, please sign up to our website and on our website.
Well, I think we do need to move on, but thank you again,
Yeah,
Sam, and it really is exciting. Our next presentation is by Caitlin, and she's going to tell us the outcome of the scavenger hunt that was held this week. Thank you.
All right, so some of you guys may have seen the rotating slide advertising student scientist and career scientist scavenger hunt. And the idea here was to encourage or kind of icebreakers for student scientists and career scientists to have interactions. So as students or as career scientists, you may have had people coming up to you and asking you, have you ever seen a penguin? But each sheet had about 10 items that students needed to find, and there were different items for the student scientists and for the career scientists. And then we collected all the completed sheets, and of the completed sheets, we randomly selected who the winners were. So for the student scientists, our winner is S. Jaya Raman. I apologize, I didn't put your first name there. I couldn't read it on the slide, on the sheet. So if you're here, could you come up? Oh, come on up. And then the career scientist winner is Anastasia Newhart. Are you here? Yeah, come on up. And yeah, so the prizes this year were a space-themed Lego set, which will look very nice in your office. I really liked them because they had atmospheric layers in the postcards. And then this was kind of an experiment this year, so if you have any feedback for me on how it went or didn't go, I'd really appreciate your feedback. So thank you. And congratulations to our winners. Thank you for participating.
Thank you, Caitlin, for organising that, and thanks for everybody who participated. You know, the idea was to get people interacting, and I think it was a great thing. So thank you, Caitlin. So our final presentation for the morning will be by Christina Lynch, and she'll be discussing the process by which we might embark on looking at a new CEDAR strategic plan after the decadal survey comes out. It's been more than 10 years since the previous one. The previous strategic plan was really excellent, but you know, we should at least have a look and see how our field has advanced in that time, and so Christina will tell us about that.
Thank you. So Caitlin and I on the CSSC are tasked with starting to get this group thinking about planning for our strategic planning. So the idea is to think about what do we want CEDAR to be. It's been 11 years since there was a very brief addendum to the strategic plan, and 13 years since the actual CEDAR New Dimension document. This year we have the decadal coming out, and so it seems an appropriate time to reconsider, review, update, and refocus what it means to have an organization like CEDAR, what it's useful for, what we can use it for. There is a document. It's on the CEDAR page. How many people have read it? How many people know about it and have never found it? How many people had no idea it existed? Okay, well, it's on the CEDAR page. It's a little hard to find. If you pull down the About CEDAR menu, there's a little piece on the menu that says Strategic Plan, and that takes you to this page. And what you want is the second one, the June of 11 CEDAR strategic document. And that's the large document that was written in 2011, Jeff, I've lost track, 2011, yeah. And then the authors of that wrote it in such a way that it could have addenda added to it. So there's a very brief one from 2013, but it's only half a page. So the major document is this New Dimension document. So I've asked Jeff, as one of the lead authors, to come and give us some thoughts about this. I wanted to ask him to think about why did the community see the need for this document at the time? Does he see that need or a different one now? And what path does he suggest for our CEDAR community at this stage? So I'm going to ask him to talk for a few minutes, and then I'll come back.
Thank you. So I was asked to look into this past history to help in the future. We have to look back in order to look forward at times. And so I went back to my 2008 presentation that I gave, and this is the slide. These are the slides from that presentation. Let me just jump way ahead. There's some history here. Actually, that's where the, let's keep going. Sorry. So we were talking about the CEDAR program, the history of CEDAR program at that time. And what I want to remind people is that there was an original document of CEDAR, and I don't know if that's on the CEDAR website, but we should have an archival of all of these documents that were generated over the years. This was the first, and it was done back in the late 80s, and it was a great articulation of what the future was looking towards with regard to ground-based observing of this environment. It was followed up by an interim review document. It was then, there was a big push for the Polar Cap Observatory, which is RISER now today. But at the time, we were making heavy pushes to create this new observatory that came into fruition, and it took a lot of work to make those things happen. Then the CEDAR Phase 3 document was released in 1997, and this was Jeff Forbes and the steering committee at that time putting out a great document that was providing that history. We did a LIDAR Beyond Phase 3 report. There was a report for self-assessment of the passive optic aeronomy. There was a ground-based upper atmospheric facilities document for the incoherent scatter radar community. And so, as you can see, we go through a lot of, as I mentioned yesterday, planning is everything, and that was a demonstration of that. It's a grassroots community. It needs to come from people who are motivated and see the need to push, and it's so important that we push forward and be strategic and promote our research. I think it's difficult to answer the questions of whether you all think we should be doing this again, where we think we are. I think we really do need to continue to gauge and determine the pulse of the science, but also what's happening within the agencies. CEDAR has grown so much. The steering committee is made up of a collection of people who span the various disciplines that make up the science we do. And it's those people that we look towards to see whether there's, within each portion of CEDAR that there's a rising need to further elaborate or investigate what to do next. The other thing to realize is that, we have to get funding. We need to help the NSF program managers to move initiatives forward. And I think that, and again, that's all has to do with what's the environment at the time. And so I'm not going to really be able to answer whether you all should do another one, but I do encourage that we strategically plan all the time, and whether that means a full rewritten document or an addendum or some other initiative within the CEDAR community, I think that has to come from the grassroots of all involved, and so that's where I would, I would promote that. I also would say that the steering committee, because the CEDAR meeting has gotten so large, the steering committee gets so involved with just the meeting itself, and which was an awesome meeting this week, and it takes a lot of effort by those members of the steering committee, and it's greatly appreciated. But you'd like to be on a committee that you're doing actually something a little bit more than running a workshop, and so I think that it would be great to see the ideas that percolate up through that body and see what that can come next. So I think it's the unique position that we are in a grassroots environment to be able to put forth what we think to do next and to be able to leverage that into the NSF's Geospace program. So I'm going to stop there. I didn't really answer anything. I gave some history. I feel like a little bit like a curator of the CEDAR thing this week, but that's cool. Yeah, I'm happy to help in any way. So I say, though, let's go for something. Whatever that might be.
So Leanne, can you come back to my slide? Yeah, okay, all right. Yeah, I think it's important for us as a community to think about who we are and what we want this CEDAR community to move with. It's not just a thing that's there that we just ride along with. It's us doing it. So it's a time to think about that. So how do we go about this? So it's been interesting this week talking to people who went through writing the visions document 13 years ago. And often the immediate response was, why would you want to do that again? It's an enormous effort. And you just got done writing the decadal. And so I think this is the schedule that we're proposing. And so one is to await the decadal later this summer. And in parallel with that, all of you who have never read the visions document should read it and see what it says. And then over this year, I think we'll collect community input through some sort of Google form or other asynchronous collection point. And definitely not looking for white papers. We don't want to recycle the data collection we did a year ago for the decadal. And it's more asking for input about, does the decadal capture CEDAR community thoughts? Are there things in the decadal that we as a group want to echo and amplify and focus? So that's a question. A separate thought is, does this 2011 document still resonate? If you read it, do you say, well, that's a nice piece of antiquity? Or do you say, well, no, that's where I am still, and I think that's a little dangerous. We don't want to say that we're exactly where we were in 2011. Presumably, we've gotten somewhere, and we want to refocus it and update it, change it. And I think we've got maybe a year here to collect those thoughts, organize them, and the idea would be to plan a session this time next year so that we can review, define, update, focus, get the voices of all the younger half of the room here into the room, and plan a session this time next year to pull together this input and formalize a response and a plan, which could be, as was done in 2013, a half a page saying, yes, that's a great document, it's perfect. Or a 5-page addendum that takes those general ideas and adds a few things to them. Or if we really decide it's time to rewrite the whole thing and start over, we make a plan for that. My guess is we'll be somewhere in the middle there. But I guess the message to get across, especially to the people coming in, is that CEDAR is not like a thing that's there and you just do it. CEDAR is us, and it's time to think about what we want it to do. So, thank you. Look for requests for feedback, and on we go. Thanks.
Thanks, Christina. So, yeah, we're not quite sure how this will play out, as Christina has said, but I think it is time for us to at least reevaluate. So, time for a quick question or two for Christina, if there are any, or comment. Absolutely.
One thing is that there was if you might recall, between the time this document was written and now, there was a portfolio review within the National Science Foundation for the Geospace program. And with that review, what they used heavily was the decadal document that was written in 2012. So I think the review was somewhere around 2015 or something like that. And so they used heavily the decadal. And so as you were saying, the decadal has now been hopefully released this fall. you know, I think we have to look at that to see what it says with respect with respect to our interests in this community, and see how much we leverage from that. But it was a shift, I would say, when the portfolio review was done, and there's obviously people here who are on that portfolio team, that there was a bit of a shift into the use of the decadal, and maybe that's something we want to be aware of. So.
In terms of timing and so on, I think it's important, especially for people who haven't been involved in writing some of these documents, to recognize the difference between something like the decadal and this CEDAR vision document, which is, you know, what the scientists think are the important science goals to be propagated. And then on the other hand, something like the portfolio review from NSF or the roadmap from NASA, which is how the agencies then implement that. And so I guess I'm thinking of this visions document is much more along the lines of the decadal, right? We're taking the decadal, all of us put a lot of effort into that, and maybe amplifying and focusing the parts of it that have to do with us. But it's that class of document. It's not a roadmap or a, what's the NSF one called? What is the NSF one called? It's not a portfolio review or a NASA roadmap. It's a science vision document. Yeah.
All right, I think we should thank Christina once again for that. And let's see, I get to introduce our final speaker, which is me. All right, well, it's time for closing remarks for CEDAR 2024, and it can't possibly be 6 days gone already, can it? I mean, standing up here, it feels more like about 37 years, I think. So, I blame Jeff myself. He's somehow blown a hole in the fabric of time. It's just, nothing works the way it used to. This has been a great meeting, so I just want to go through and a little bit of a review of what we've done and thank a few people and introduce the new incoming CEDAR Science Steering Committee members. So let's see. Oh, I've got to figure out how this works. There we go. So just some statistics on our meeting. I gave this same talk last year, and I look back at the talk I gave, and I had a big highlighted title that said last year's meeting was the biggest ever with 420 registered participants. So I guess we beat the record by one this year. I haven't checked all the other numbers, but I guess we had 140 student attendees, 196 posters, of which 144 were submitted by students, 105 in the competition. We were able to support 99 students, which I think was many more than we had originally imagined, but we were able to do that, so that was great, and lots of sessions there. 6 plenary sessions, 43 individual workshops, and we had to merge several to achieve that. Just a couple of pictures here. That was our panel on the Grand Challenge workshops at the top. That was, I think, very well received. I've heard lots of positive comments about that. And then the picture below shows our student poster prize winners. So one of the things I get to announce here are the who is leaving the CEDAR Science Steering Committee this year and who are coming on. So I think I really want to acknowledge the work of our CEDAR Science Steering Committee members who are rotating off: Matt, Sue Wei, Lindsay, Andrew, our student rep, Jia and Ying. They have all helped the CSSC and myself tremendously in the last year, and I'd like to give them a round of applause. We have new members rotating on. I'll read the names out, and then I have photos on the next slide. So we have the new members coming on are Erin Lay, Gareth Perry, Luis Navarro, Romina Nukoka, Bea Gallardo-Lacourte, Shenrong Zhang, and Michelle Buey. I demonstrated my inability to count because we've actually got a couple more coming on than going off. But that's actually useful because we've got so much to do in this coming year with trying to organise a CEDAR GEM workshop and looking at this strategic plan. So I think this will be really good. These are the photographs of our new members coming on. I'm very excited to work with them. One other thing we do, one more thing I have to announce. The way we do this is that we have a CEDAR Science Steering Committee chair who is appointed to overlap with the incumbent chair for 1 year. And so in 2022, I was appointed and I overlapped there for a year, and that was fantastic. And so now, this being my 1 full year as the sole chair, it's my job to announce the chair-elect that we have coming on, and so someone should probably bring an envelope up here so I can read the name out, but I'm very pleased to announce that our new chair-elect is Lynn Harvey. Maybe I could ask Lynn to come up and just say a word or two. Oh, you've just...
I have planned 0 remarks. You know, this is such a great opportunity. I will do my absolute best to guide this community through its next several meetings and through the evaluation of the strategic plan and where we go from there. And I look forward to meeting a ton of people and learning a lot.
Thank you. Yeah, thank you, Lynn. And I should say that the way this is done, we have nominations for possible incoming chairs, and we had a number, and I think the CEDAR Science Steering Committee felt that any one of our nominees would have been fantastic, but Lynn was the one that everybody felt would be our best leader to come in. So I'm really excited to work with Lynn for the next year. You know, when I started, Larissa mentored me for a year, and I had no idea what I was supposed to do, and she was a fantastic mentor, and I should thank her for that. And I'm hoping to be able to do as well to help Lynn come up to speed. A couple more pictures. This was our CEDAR Prize speaker and DEI speaker. Both were fantastic talks and a really good part of our workshop. We collect feedback. We're always interested in feedback, and I put this slide together just with a few things mostly that I have heard. I think there's quite a lot more feedback than this, but some of the things that I personally had heard that I remembered hearing as I put this slide together, comments that struck me was that the plenary panel we had up here for the Grand Challenge workshops, a number of people spoke to myself and other CEDAR Science Steering Committee members saying how they liked that. Many people like San Diego. It's a great place and fortunately not too hot. One issue that I have heard is that San Diego is a little bit expensive for students to do things outside of the meeting here, and that's something we should be cognizant of. Another suggestion I heard is that if people find it a little difficult with our agenda. You can look through the agenda, but if you wanted to produce a table of all the places I can hear a particular speaker or go to see a particular speaker, there's not a way to generate a good report there, so we might have a look at that. I heard a comment that at the mentor lunch, some of the tables didn't actually have a mentor present at that table, so maybe we can try and address that. And I've heard lots of positive comments about the CEDAR GEM, our attempts to organise a CEDAR GEM workshop. So everybody seems excited about that. There's lots of other feedback. These are just a couple of things that occurred to me last night as I put this slide together. This is our distinguished lecturer, Jeff. Just a picture of him at the end of his talk there. I really want to recognise the work done by our student representatives in the last year, Andrew and Sophie. They were absolutely outstanding in just organising the activities here and participating in all of our CSSC planning. They did a really tremendous job, and I think we should give them a round of applause. And so, of course, Andrew's rotating off, but we have a new rep, Michelle, coming on, and so Sophie and Michelle will take the helm for the next year. This was the outreach talk there. very nice talk that we had for the outreach. And I really just want to finish with a slide. I put up a bunch of names. I apologise if I have missed somebody. I tried to think of all the people I wanted to thank. But in particular, I personally want to thank Li Ying, because we couldn't do this without her. Fantastic support there, so I think we should... All the various members of the CSSC have contributed to this meeting. The DEI task force have done a lot of work behind the scenes, and I think we've seen that this week with the DEI activities and the breakfasts and what have you. All the people who convened workshops, that's been fantastic. And I'd also like to thank the staff here, the AV staff and the catering staff and the people in the hotel that make this possible. So thanks, everybody, and hopefully... this is from the banquet last night. The banquet was great. One thing I neglected to say at the banquet is that, our 5 students who came up and gave that talk, I said to a few people afterwards, I think fewer than half the people, not many of the people in the room, could have got up and presented that talk with such grace and unfazed to get up and tell the story and answer the questions. It's quite an intimidating thing to stand up in front of 400 people at a banquet and give a talk like that, and our students did a great job. So thanks for that, and see you all at CEDAR Gem next year. Don't forget there's still 4 great workshops to come, and that will be the conclusion of our meeting, but see you all next year. Thank you.